All right, let's dive in. We're about to pull back the curtain on a class of chemical compounds that are, well, hiding in plain sight. They are the secret engine running some of the most important processes in the world, connecting things you'd never think were related, like our own blood, the leaves on trees, and even our vitamins. So let's get into it.
So let me just start with a question for you. What on earth could your blood possibly have in common with a green leaf? Or with something like vitamin B12? I mean, on the surface, they're completely different, right? One's carrying oxygen around your body, one's capturing sunlight, and the other is just keeping you healthy. And yet there's a fundamental chemical secret they all share, a structure that makes them all work.
And that hidden connection? It's a special kind of molecule called a coordination compound. At the heart of hemoglobin, you'll find an iron atom. For chlorophyll, it's magnesium. And for vitamin B12, it's cobalt. It's this incredibly specific structure that gives each one its unique and vital power.
Okay, so what is it about these compounds that makes them so special? To really get it, we've got to look at how they're put together. So let's break down their basic anatomy and kind of build one from the ground up.
Every single coordination compound has two main parts. Right in the middle, you've got a central metal atom. The easiest way to think about it is like a key ring. And then, attached directly to that ring, you have a bunch of other molecules or ions. These are called ligands. So the ligands are like the keys, all hanging off that central ring.
Now that whole package, the central metal atom and all of its attached ligands, that's a single unit called the coordination sphere. In chemistry, you'll see it written inside square brackets because it really acts like one solid thing. Anything you see written outside those brackets, that's what we call a counterion, and it's really just hanging around to make sure the overall electrical charge is balanced. So the coordination sphere is the whole keychain, and the counterions are kind of like a little decorative tag hanging off it.
For a really long time, this whole structure was a complete mystery to scientists. I mean, how did these things even hold together? The answer finally came from a Swiss chemist named Alfred Werner, who, back in the late 1800s, basically solved the entire puzzle before anyone even had the modern theories to explain why he was right. And you know, he worked shockingly fast. Werner developed his entire groundbreaking theory in what was basically a flash of genius between 1890 and 1893. He then had to spend the next 20 years proving his idea to a very skeptical scientific community, finally winning the Nobel Prize for it all in 1913.
So how did he do it? How did he prove it? Well, Werner was experimenting with these cobalt compounds, and he noticed something really weird. Even though they all contained the exact same elements, they acted differently. When he ran a test, the yellow version of the compound lost 3 chloride ions, but the purple one lost only 2, and the green one lost just 1. It made absolutely no sense. Why was this happening?
Werner's big insight was just brilliant. He proposed that metals must have 2 totally different kinds of bonds, or valences. The primary ones, he said, are weak and can be broken. Those are the chloride ions that were outside the brackets. But the secondary bonds, those are the important ones. They're strong, they're directional, and they lock the ligands inside the brackets into a fixed 3-dimensional shape. And just like that, it all clicked. The chlorides locked inside couldn't react, while the ones outside were free to go.
This idea also solved another huge mystery of the time, isomers. You see, isomers are compounds that have the exact same chemical formula, the same atoms, but they have different properties, like color. His green and violet compounds were isomers, and Werner realized that if those ligands were locked into a 3D shape, you could arrange the very same pieces in different ways, and that different arrangement would create a totally different compound. It was genius.
But for all its brilliance, Werner's theory couldn't explain one of their most obvious features, their incredible, vibrant colors. Why is a ruby red and an emerald green? To answer that, we have to jump forward a few decades and take a little leap into the quantum world with an idea called crystal field theory.
Okay, here's the simple version of how this works. When white light, which contains all the colors, hits the compound, those ligands create a very special electrical field around the metal. This field splits the energy levels of the metal's electrons. This split is just the right size to absorb energy from one specific color of light, which lets an electron jump up to a higher energy level.
So the color that we actually see is just whatever's left over. It's the complementary color to the one that got absorbed.
So if a compound absorbs yellow light, our eyes perceive it as violet. If it soaks up red light, we see it as blue. It's a bit funny to think about, right? The color of a gem isn't the light it takes in, it's the light it throws away.
And this just proves how critical those ligands really are. Without them, there's no color, period. Take anhydrous copper sulfate, for instance. By itself, it's just a boring white powder. But the moment you add water, those water molecules swarm the copper, acting as ligands, and instantly, boom, it turns this brilliant, vivid blue. The ligands literally bring the color to life.
So look, this isn't just some fascinating piece of abstract chemistry. Understanding this structure allows us to actually use these compounds to solve major real-world problems, from medicine and industry all the way back to our own biology.
I mean, the list of applications is just wild. We already talked about the biological powerhouses like chlorophyll and hemoglobin, but beyond that, they are industrial workhorses. We use them to purify metals like nickel, to speed up chemical reactions, to electroplate gold and silver onto jewelry. In medicine, a platinum compound called cisplatin is a crucial anti-cancer drug, while another compound, EDTA, is used to literally pull toxic lead out of a person's body. They're so useful, they were even a key part of old-school film photography.
And this quote really sums it all up, doesn't it? The coordination compounds are of great importance, widely present in the mineral, plant, and animal worlds, and are known to play many important functions. They're not just some random topic in a textbook. They are a fundamental building block of our world.
Which really brings us to one final big question. We've gone from not even knowing how these molecules were shaped to being able to design them for incredibly specific jobs, like fighting cancer. So, what's next? Now that we understand how to build these tiny molecular machines with such precision, what are the next global challenges we could solve? Better catalysts for clean energy? New, more powerful medicines? The possibilities are really as vast as chemistry itself. Thanks for joining me on The Explainer.